to the colors, to the sounds, and wanted to tell everyone what he saw. Unfortunately, what the others who were still tied there could only hear was, again, distorted voices and shadows. The meaning from this is that what we see might be just a fraction of what there exists. There might be a lot more in the background. It was an amazing way of thought back then, amazing. So, a long time ago, I was going to higher school, and I had some huge glasses. I'm so ashamed I didn't even put a picture over here because it was very big. So then somebody called me, hey, you look like four-dimensional. After that, I got into four-dimensional stuff, and I wanted to learn what it was. So this guy, I remember him. If I find him when I go back to Greece, I want to thank him. So there's a theory, then we use some symmetry, and I can try to bring some nice structures. So I won't go into detail regarding what's written here. I'm just going directly to the theory. Of course, I cannot claim that there are four-dimensional things. There are four-dimensional symmetry things. There are three-dimensional objects which are projection of those four-dimensional structures. But because they can change shapes every time, we can see something as close as possible to the four-dimensional. What I mean is this: if we had a cube going through a two-dimensional world, the people will see the slices, the projection of the cube, right? So by moving those things, I get 4D shapes which are projected into 3D world. So I get a collection again of shapes, which gives me an idea of what this four-dimensional object might look like in my imagination. So, well, the construction was interesting. I had to use some telescopic rods, but I'm going to go into that in more detail later. So, but how to make them in such a way so when I move them around, for example, this guy here, the simple one, I can move him around and nothing will break. How can I do this? Well, it can be done by dividing it into some simple polygons, like triangles or squares. Triangles are very effective, or in the case of the hypercube, where you can only use squares, or even you can use some other shapes as well. We'll see this later on. So I call them graphitrons. This is the name that I've given them. And there is this move, they have the inside-out move. If you look at this little guy here, we have a tetrahedron, it's three-dimensional. If we have as I said to you before, we have a green, yellow, purple. Everywhere. Green, yellow, purple. How can I make it green, green, purple, yellow? I just have to move it inside out. And then everything changes completely automatically. Now, with those structures here, this is more impressive in some sense. While it looks trivial to the three-dimensional, those do it in a much better, let's say, puzzle way. So, this is an example for the pentahoron. This is a pentahoron. So look how it moves. The vertex A, the corner A, goes underneath the CBD, the blue one, and then it goes through this space here, it comes out, and then we have a different configuration. So you can see that we can virtually place in the middle, any of those rows can go into the middle. So if I color them with 10 colors, any color can be eventually in the middle with the correct manipulation. So this is a pentahoron which is based, this is a pentahoron here, the one you showed before. This is a pentahoron here. And it's vertex transitive, has some very nice symmetric properties, and edge transitive as well. In the case of the hypercube, this is vertex transitive, but it is not edge transitive, unfortunately. But it's okay. We still love it. And in the case of the hypercube, we have a cube, small cube inside a big cube. But which is a small cube and which is a big cube? Because this small cube can go outside, and the big cube can also become small and go inside. And this is a movement that is done. We have not only one corner, but 4 corners that go together out each side.
Can you actually do that with this?
Yes. So I'll do this very fast. It doesn't take much time actually. I just have to make this one small, and then this one small, those ones I have to make them bigger. So I'm halfway now here, before the black was out. Now we have half now is halfway now. And if I continue, if I make this one small now, this one small, this one small, I have to do it twice. I'm going to move this one out by doing this movement. We have that the yellow one is coming eventually outside. It's a good structure, this one. I like it a lot because it's quite strong. And okay, so the black one is just a matter of calibrating now, making the rods a bit smaller. And, but you can see that the black tube now is inside. And this one, and this one, and still in some calibration.
Nice.
Thanks. And so this is a hypercube. So we need, of course, some flexibility. Otherwise, we won't be able to achieve anything. Because it has orthogonal properties, it's much more easier to use this one. This one I need to use some swivels as well, so it's a bit more complex. Because the triangular nature of this structure is requiring more complex movement than the hypercube corners. So this is another, it's not a polytope. This is not, just like we have 5 platonic solids in 3 dimension, we have 6 something similar polytopes, as we call it, or polyhorons in the 4 dimensions. And this is not one of them. But it's also nice to see that it can be applied here as well. We have a triangle, so a tetrahedron is another tetrahedron. And eventually, by doing some movement, they can change colors again. And I have a prototype for this one, not with me, but I do have a prototype for this.